Did anybody look at this video for that assignment? The one on how tall buildings tame the wind? No? All right, well, you'll get, we're not going to watch the whole thing in class because it's like 10 minutes long, and can't spare that many minutes, but we'll watch some of the interesting parts that are specifically related to how wind interacts with tall buildings, and you'll see some CFD simulations showing the flow of wind around tall buildings, and specifically they're going to be talking about a phenomenon called vortex shedding, which is something that tall buildings are specifically susceptible to, and that's where the wind, if it can get organized along the height of a building, it will basically have the effect of pummeling the building back and forth. So the wind can be moving in one direction, but the building is actually swaying in the opposite direction, back and forth, due to this vortex shedding phenomena. So it's an interesting phenomena, and they're going to talk about some strategies that we use to mitigate that effect. All right, so we'll look at that.
This allowed sunlight to reach street level, whilst breaking up the facade and reducing the impact that high winds had on these early towers. By the 1960s, however, larger box-like skyscrapers began to come to prevalence, bringing with them a whole host of wind load engineering challenges. The first problem that began to arise was increased wind velocity at street level. This was principally caused by the street canyon phenomenon, an effect that sees large buildings redirect wind down their facades, which effectively act like canyon walls, and funnel it along streets at much higher velocities than in low-rise suburban areas. The street canyon effect was particularly notable in Manhattan, where the heavily formalized grid structure of the city blocks offered little to break up and deflect winds once they began to blow. Additionally, as wind moved around the top of these tall structures, vortices were being created in a process known as vortex shedding. This process, much like water flowing down a stream, acts differently on obstacles depending on how streamlined they are. In the case of these buildings, their sheer block walls created a bluff obstacle that wind had to flow around. As strong winds moved around these structures, areas of low pressure emerged on the opposite side of them, creating suction forces that pulled at the buildings, causing them to sway back and forth. While any such movement may initially be minimal, high winds can create vortices that can match the frequency of the building they are moving around, causing noticeable swaying and shaking motions for those inside. This phenomenon led engineers to begin testing models of tall buildings in wind tunnels at design stage, assessing the potential impact of high winds on structures before they were constructed. By doing this, project teams were able to develop innovative approaches to managing wind loads, reducing their impact on tall buildings and enabling them to rise even higher. The first and by far simplest way to reduce the impact of high winds on a tall building is with an approach called corner softening. Corner softening sees sharp edges smoothed off of a structure to make it more aerodynamic, or small cutouts created on the edges of a structure to scramble prevailing winds and reduce the strength of the vortices they create. A prominent example is the ornamental design of Taiwan's Taipei 101, where relatively minor cutouts on the building's corners reduced movement by as much as 25%. Tapering a building as it rises also breaks up the uniformity that causes vortex shedding. Kuala Lumpur's Petronas Towers and the Shard in London both use this technique to reduce the effect that high winds have on their structures. Taking things a step further, alternating a building's profile as it rises, and including setbacks, can also reduce the strength of vortices as they move around buildings. Some of New York City's early skyscrapers achieved this in response to the setback ordinances of 1916. But perhaps the most notable example today is the 828-metre Burj Khalifa in the United Arab Emirates, the world's tallest building at the time of filming. This remarkable structure uses a range of techniques to tame the wind and achieve its height, including an extreme taper, multiple setbacks, and a high degree of corner softening. We've demonstrated how the Burj Khalifa's carefully crafted design manages the wind in this simulation, developed using SimScale's software. With more than 150,000 users worldwide, SimScale is an easy-to-use, cloud-based engineering simulation platform that enables everyone to create powerful, high-fidelity simulations in a web browser.
So basically what's happening here is you can see and they're showing some snapshots of different levels along the height of the building, what the plan shape looks like. And you can see those vortices forming at each plan shape, but the takeaway is that because that plan shape is changing with height, those vortices can't organize along the height. So they get broken up, and so their effect gets mitigated. So it's a really effective
The
solution.
platform can be tried for free through the community account, which gives access to thousands of public simulations to promote knowledge sharing and to crowdsource advice. Creating a twist in a building's form can also reduce the impact of vortex shedding. With every floor offset to the last, the number of bluff areas across these structures is considerably reduced, minimizing, or in some cases completely eliminating, the locations where vortices can form. Perhaps the most breathtaking example of this technique can be seen in China's megatall Shanghai Tower, which tames the wind and rises to become the world's second tallest building by elegantly twisting throughout its 632-metre height. Another way to reduce the impact of high winds on tall buildings is to increase their porosity, cutting out parts of the structure and allowing air to flow through as well as around the building mass. This technique has been used in a number of high-profile skyscrapers around the world, including Saudi Arabia's Kingdom Center and the World Finance Center in Shanghai, China. But the most impressive example can be seen in New York City's 432 Park Avenue. With an incredible width-to-height ratio of 1:15, the tower is one of the world's most slender skyscrapers and the most prominent manifestation of New York's emerging super skinny residential tower trend to date. The 426-metre tower features double-floor cutouts at 12-storey intervals throughout its height, allowing wind to pass through as well as around its extremely thin structure. We have again demonstrated the impact of this approach in a SimScale simulation. Some buildings using this approach have tried to incorporate wind turbines into their voids in an effort to harness wind energy and convert it to electricity. Despite the obvious benefits of this, wind turbines on skyscrapers never really seem to have caught on. In addition to the
That's because it's not actually that efficient.
techniques that tall buildings use to tame the wind, some are also fitted with dampers that counteract motion where it occurs. These incredibly heavy instruments are suspended, often on the upper levels of skyscrapers, and sway as buildings move, counteracting motion and creating a more stable environment for those inside. Several tall buildings already use these dampers, including Taipei 101 in Taiwan and the Trump World Tower, 432 Park Avenue, and 53 West 53rd Street in New York City. The advancements in wind load engineering made over the last 100 years have enabled the incredible skyscrapers we see today to become a reality. With further research underway and an incredible range of new technology innovations currently entering the construction industry, we could see tall buildings rising even higher in the years ahead.
All right, so those damping devices that they were just talking about, the tuned mass damper that they said Taipei 101 has and such. So now the United States is starting to incorporate that approach a little bit more, but historically, other countries, especially particularly in the East, have been more advanced in embracing that type of technology to reduce the accelerations and motion of tall buildings. Culturally, in the West, we're just averse to it. So, a lot of times these solutions would be proposed to clients and building owners, but they would say, oh no, because if I have a device in my building that is supposed to stop it from moving, that means the building's moving and people are going to panic and freak out. And that's true. That's what would happen. So they would just be like, no, we don't want that. Just make it so that it doesn't move a lot. So we can do that, but it's a nice, convenient way to incorporate a device like that so that you can build a more efficient structure ultimately. So anyway, we're starting to embrace that now a little bit more in this culture. Yeah.
What they do for the Twin Towers, because those don't really have a lot of deformities or like tapering or anything.
Right, so the World Trade Center Twin Towers, those were moment frame structures, and they were built designed in the 60s, built in the 70s, I think they were completed in the early 70s. So those buildings, for wind, and that was probably early on in the wind design, so kind of before some of these techniques were fine-tuned specifically for wind. Like in the video, it talked about how the setbacks were first achieved just through city ordinances. So the original purpose for those setbacks had nothing to do with reducing wind speeds, but it had that effect. So for the Twin Towers, they didn't have the setbacks. It was just one geometry all the way up, right? So I don't know if they had any particular strategy for those towers to reduce wind, actually. As far as I know, there were no damping devices installed. They had a core, so the building had a core and then moment frames, and then there's a cap truss on top of the building that tied the perimeter moment frames to the core. So I don't know if they had any specific strategies for reducing wind loads. Good question though. Yeah, any other questions? Okay. Cool, so I thought that was a pretty interesting video. Thought it was worth sharing. And I think, I think I showed this for those of you that took dynamics last semester. I think I showed you this. So just as a refresher, this is showing wind tunnel test demonstrating that crosswind phenomena. And so you can see the building and all of those techniques that they talked about in the previous video, corner softening, putting in cutouts or setbacks, twisting or changing the shape of the building as it goes up. We say that all of those have the effect of confusing the wind, so it can't get organized and create that vortex shedding phenomena. So, pretty neat stuff. All right. So now we're going to move on to, that's not the correct slide. All right. Skipping ahead. Ignore the exam info. That was from last semester. So it'll be similar for our exam too, but not exactly the same. All right. So continuing on with the snow loads. So we're going to start off, again, kind of going through these lecture slides, which will introduce the general approach to determining snow loads for buildings, and also it will talk us through the ASCE environmental loads handout portion associated with snow loads, which that will be the last chunk of this handout. So starting on page 30 with the cover sheet, and then going to the last page in that handout, we'll cover snow loads. So we'll introduce that, and then the rest of the snow loads lecture will be focused on example problems, so we'll probably get to that on Monday next week. So let's see. All right, so snow loads, we have to think about this on any surface of the structure that can accumulate snow. So generally roofs, decks, balconies, things like that. These snow loads that we determine, right, as with our other environmental loads, are a function of the geographic location of the structure. But for snow, we also have to think about how sheltered is the roof, all right? So that what comes into play there is things like how many trees are closely surrounding your building, what kind of trees are closely surrounding your building, are there no trees, what kinds of buildings are around, right? Things like that. The roof surface material, right? So that can play a big role. If you got a typical shingled roof, the snow will be, no matter how sloped it is, the snow will be less likely to slide off compared to a roof that is metal sheets, right? So, and a lot of times around here, especially in the valleys like Gallatin Canyon and Bridger Canyon, right, where snow can accumulate significantly, you see a lot of roofs that are either pretty steep and or have these metal surfaces, right, where the snow can just slide right off. So that's intentional to help reduce snow loads. The slope of the roof, of course, right, steeper slopes will shed more snow. And then the use of the building, as with our other environmental loads. So before you calculate snow loads for any type of roof, you have to evaluate or determine what is the flat roof snow load for that structure. So even if the roof is sloped, we still have to calculate this flat roof snow load first, and then we'll make an adjustment for any slope that exists. So the code, or the ASCE standard, in the context of snow loads, defines flat roofs as being anything up to 5 degrees in slope. All right, so remember, this is a little bit different from how we distinguished between roof slopes in wind loads, because with wind loads, what was relevant, the relevant cutoff was 10 degrees, right? So that was for steep roofs versus shallow or flat. For snow loads, the relevant cutoff is 5 degrees, so that's anything less than that, including that, is considered flat. And this is the equation for determining flat roof snow load. And that would be, if your roof is flat, that would be the design snow load that you use for that roof in pounds per square feet. So these factors that are contributing to that value are defined here. We've got CE, which is an exposure factor. That's something that we would obtain from one of the tables in the handout. And we'll look at that more closely in a moment. The exposure factor accounts for the exposure of the roof and also the surrounding terrain. It takes into account, the ability of wind to remove snow from the roof, and things like that. So then the next factor is a thermal factor, also something we obtain from a table. This accounts for whether the structure is heated or unheated, right? So most buildings will have a thermal factor of 1 because they're heated for occupancy. But if you have, for example, a greenhouse that's continuously heated, then you would have a smaller thermal factor because you would want to reduce those snow loads, because that continuous heating would tend to have the effect of melting the snow off the roof. Or if you have a cold structure that's not heated at all, then you would have a higher CT factor to increase the snow loads. The importance factor for snow, right, similar to the importance factor for seismic loads, we get from that same table on the first page of your handout. All right, so if you look at that table, this one at the bottom, seismic loads was on the far right. The snow loads is the first column on the left, following the risk category that you enter with. And The last item in that equation is PG, which represents the ground snow load. So the ground snow load is what accounts for the geographic location of the building, right? So these are mapped values that we obtain, and it also takes into account, right, the typical density of snow for your region, right? So for example, here in southwest Montana, the snow that we see tends to be less dense than snow you would see in the Pacific Northwest, for example, right, where it tends to be a lot heavier, more wet. So some states, we'll see this, have tables instead of using mapped values, and so you would want to refer to the table instead. And then always, as with other loads, you want to consult the governing jurisdiction and make sure that you understand what kinds of minimum values they might issue. So the minimum value required by the jurisdiction having authority might be larger than whatever you would obtain from these tables or mapped values. All right, so ASCE 7 does prescribe some minimum values that are related to snow loads. Specifically, if you have a low slope roof, right? And in the context of snow loads, a low slope roof is anything 15 degrees or less, right? So flat roof, 5 degrees or less, low slope, 15 degrees or less. So if you have a low slope roof, then these minimum values will apply. Or I guess technically it's one minimum value. It just depends on what your ground snow load is. All right, so if your ground snow load is 20 PSF or less, then the minimum snow load that you can use would be the importance factor times that ground snow load. If your ground snow load is greater than 20 PSF, then the minimum snow load that you can use would be 20 times the importance factor. And that would just apply to low sloped roofs, right? So first you would calculate your flat roof snow load using the equation we just talked about on the previous slide. And then you would determine, if you have a low slope roof, you would determine what this minimum value is based on your ground snow load. If the value you calculated for the flat roof snow load is less than that minimum, then you have to use the minimum value. And that's also, of course, in addition to checking any local criteria or local minimums. All right, so now if you have a sloped roof, right, we consider the snow on a sloped roof as a uniform load acting over the horizontal projection of that roof. So snow is essentially a gravity load, right? You're designing for the weight of the snow on your roof. So the resultant direction of the snow load will always be in the direction of gravity, right? So because of that, right, you've got the arrows. I think I have it on the next slide, actually. Yep. So on your realistic representation, right, it's not going to be a perfectly uniform depth on your roof, most likely. Sometimes it might be, right? But most likely it won't be perfectly uniform. But we can idealize it as a uniform snow load. The resultant force will be acting downward in reality as well as in our idealization. And then we can just treat that as a uniform load acting over the horizontal projection of the surface. So to calculate that value then for the sloped roof, we take the flat roof snow load that we already calculated, and then we modify it with a slope factor, CS. So this slope factor is something that we obtain from a figure. So there's a chart that we'll look at in a moment, and I'll break down for you how to use that chart. So that would be your value then for the design snow load for sloped roofs in PSF. Now going back to checking local criteria, right? So for roofs that are greater than 15 degrees in slope, ASCE minimum doesn't apply, right? The ASCE doesn't have a minimum value to check for slopes greater than 15. But your local jurisdiction will most likely have a minimum value, especially if you are in a place like Montana where we get significant snow. So the state of Montana has said the minimum design roof snow load, regardless of whether your roof is flat or sloped, is 30 PSF. Bozeman has further intensified that minimum, right? So if your structure falls within the city of Bozeman, then the minimum design roof snow load you can use is 40 PSF. Also, Bozeman specifies a minimum ground snow load of 46 PSF. So that's another thing to look out for. If you look at the mapped values, well, for Montana, Montana's now listed in a table. But in the past, if you looked at the mapped values for this area, you would pull a value of around 30 PSF for Bozeman. Maybe it was 35, I don't remember exactly. But Bozeman says, no, we have to use 46 as a minimum. So make sure that you always check the local criteria. So here's just a snippet from the state of Montana building code. Well, this isn't actually their code, it's their website where they state snow load information, but it comes from the code. So there you see it underlined down there, right? The citation for the snow load criteria of the state of Montana came from a document that was published by folks here at Montana State University. So specifically, it was Dr. Jerry Stevens, who used to be the department head, and he's retired now, but he, as well as a few others, collaborated to compile a database that is now used for the entire state of Montana. So it's now cited not just at the state of Montana's website, but it's also cited in the ASCE 7 handout. So we'll look at that as well. So here's the Bozeman criteria, right? We've looked at this page before in the context of seismic loads and wind loads, and now we're focusing on the snow load criteria. That's where you can see the basic ground snow load is 46 PSF, and the roof snow load is 40 PSF. And those are minimum values, right? So if you calculate a value higher than that, you should certainly use the higher value. So here is an example of just a nice demonstration of how this curved roof surface does have an almost perfect uniform depth to it, right? So it's a little bit hard to tell without adding the arrows, but if you add those arrows down, right, the actual depth of the snow is almost perfectly uniform throughout that horizontal projection where the snow applies. All right, so we just take that and treat it as the uniform load distribution that we're used to seeing, because it's the same thing. So here's one of those metal roofs that I was talking about earlier that allows the snow and ice to just slide right off. Here is, this was taken in Yellowstone National Park. So in the Canyon Village some years ago, they got a significant amount of snow, and this is showing the process of the snow removal. So I think that the blocks that they were carving off of this roof were, I want to say they were 2 feet by 2 feet in plan and over 7 feet tall, I think. So pretty significant amount of snow there. But you can see, right, it's a relatively flat roof. Like doesn't have a significant slope, and it's shingled. So there's not much help from the building in shedding that snow, right? So they have to use some manual labor to get rid of it. All right, so we've talked, I think I showed this at the beginning of the semester, right? Some of you may have been here for it, or at least you've heard about it. So this was the collapse of one of the gym roofs in 2019, and this followed a series of, we had some significant snowfalls and then some periods of warm temperatures, so there was some freeze-thaw activity, and after a few cycles of that, what happened is the snow, this was a flat roof, and the snow was melting on the surface, All right, so this building also had a thermal system installed that was supposed to melt the snow and then direct the snow melt towards a center drain. So a lot of times flat roofs will have some system like that. But what happened is we had so much snow and too many freeze-thaw cycles that it couldn't drain the snow melt away quickly enough. And so it ended up freezing over and it blocked the drain. And then the snow kept accumulating, and that led to progressive collapse of the roof. And so this is an issue that is addressed in the ASCE 7 standard. It's called ponding, and it's something that we have to think about for rain and for snow loads on flat roofs. So we'll look at that in the context of rain roofs again as well, but that can happen. And what happens is, I wish I had a marker, I don't think I have one here, but what happens is basically as snow or rain accumulates, if it can't be drained away quickly enough, the roof will begin to deflect, right? And the more the roof deflects, it sort of adds more capacity for snow or rain to build up above it. And so as that continues, it will deflect more, and then more can accumulate. It will deflect more, and more can accumulate, and it just keeps going through that cycle until it finally collapses. So that's what we call progressive collapse. All right, so now we're going to walk through the ASCE 7 handout. So if you have that with you, I invite you to follow along. Again, starting on page 31 with the maps. All right, so first, nice thing with snow loads is there's only one map to think about, or if you're in one of these states that are shaded red, it's a table instead of a map. So a couple things to point out here. If you're reading values off of the map, what you might see is the ground snow load shown normally, right? And then the value in parentheses. Now I've told you before that in this document, values in parentheses typically represent the metric equivalent of whatever other value you're looking at. This is an exception to that, right? So here, the value in parentheses represents the minimum elevation, or excuse me, the maximum elevation for which that ground snow load value applies, right? So if your building location is at an elevation that's higher than that, then you need to consult the local authority to determine what your actual ground snow load is going to be. So that's one thing to keep in mind with this map. Another, right, the blue shaded regions all are associated with this CS notation. So that means case study. And basically that just means go to your local authority and ask them, or find out what the ground snow load is for your location. And then some states will have no mapped values showing up on the map because they have now switched over to a table, and so you need to use the table value instead. So the tables, all right, for various states start on the next page. And they're basically broken up by, city or town, or you can look up a county. And then you've got your ground snow load in pounds per square feet. And then here's the maximum elevation for which that ground snow load value applies. So we got Colorado and Idaho, Montana and Washington. I think it's just kind of interesting to scan through these tables and compare the values. So looking at Montana, right, we can see here in Bozeman, oh, there we go, the table value is 40 PSF. But remember, the city says 46 PSF, right? But if you are in Gallatin County, outside of Bozeman city limits, you can use 40, because Gallatin County doesn't have a requirement that supersedes that, right? But if you're within Bozeman city limits, you have to use 46. So you can kind of see there, if you scan down that table, this doesn't show all of them, but the maximum value listed for Montana is in West Yellowstone, actually, and that ground snow load is 122 PSF. If we compare that to the values that we see in Washington, right, I think Washington actually has the highest values, so we've got, see, 438 near Crystal Mountain in Pierce County. And I think that's actually not the largest value in that list, though. If you scan down, it doesn't show up on here, but if you have it in front of you, in Mount Baker area, 588 PSF for your ground snow load there. So pretty significant, and that's the difference between that heavy Pacific Northwest snow compared to our, what is it, cold smoke, right? So the light, not so dense snow that we get here. All right, so then at the bottom, right, at the bottom of each of these tables, there are notes that you always want to make sure that you read the notes so that you understand the nuances of that specific table. And then the notes will also cite the source for the values that are being listed. So this is where ASC 7 cites the Civil Engineering Department of Montana State University. So pretty cool. All right, so then continuing on, you've got New Mexico and Oregon there. Let's see, I don't know, can we see? Yeah, Oregon has some significantly high ground snow loads as well, but nothing so far that tops that 588 at Mount Baker in Washington. Even Alaska doesn't beat it. Yeah, so Alaska's table is a little bit different. That one does not list a maximum elevation for which snow loads applies. So all the other ones do, though. All right, so that takes us through the complete tour of the ground snow load values. So now we move on to the exposure coefficient or exposure factor, CE. Now this table, we enter that with the surface roughness category, and that is the same surface roughness category that we looked at in the context of wind loads, right? So remember we had surface roughness B was associated with suburban areas, C was associated with like open fields or scattered obstructions, and then D would be the flat open surfaces like mud flats, ice flats, large body of water, things like that. So we use that same category, and then combined with that, consider the exposure of the roof, right, where we have three options: fully exposed, partially exposed, or sheltered. With those two pieces of information, you pick out the appropriate CE factor, all right? So it's just what I was talking about there. That's the same as for wind. The roof exposure definitions are down in the footnotes below the table, all right? So a partially exposed roof is defined first because it's just anything that doesn't fall into the sheltered or fully exposed categories. Fully exposed is defined as a roof that's exposed on all sides with no shelter that is provided by any terrain, higher structures, or trees. And then it goes on to say a few more details that you don't have to worry about in this class. And then it says, sheltered roofs are roofs that are located tight in among conifers that qualify as obstructions. So tight in among conifers, right? So if you have deciduous trees that shed their leaves, that doesn't count. It has to be closely spaced conifers that are surrounding the roof in order for it to qualify as sheltered. All right, so this is just a refresher on that exposure category, right, from wind loads. And then the next factor is your thermal factor. So this is the table where we would grab that value, and that's just based on the thermal condition of the building once it's in use, right? So what is that expected typical value? All right, so then that brings us, last but not least, to the slope factor. So this chart is on the bottom of the last page of that handout, and there are 3 steps to determining your slope roof factor from this chart. So first, you want to choose which of these 3 graphs you're going to use based on the thermal factor. All right, so the first one is for warm roofs, right? So most buildings will fall into this category with CT of less than or equal to 1. The second one is for cold roofs if your CT value is equal to 1.1. And then the third option is for cold roofs with a CT of 1.2 or larger. So if we go back to the last table, right? What's the difference between the CT of 1.1 and 1.2? The 1.2 is associated with unheated and open air structures. So that's the worst, not the worst case you can have. The worst case you can have is a freezer building, right? 1.3. 1.1 are buildings that are kept just above freezing, right? So basically not a structure that's meant to be occupied by people for long periods of time. All right, so based on your thermal factor, pick which one of these 3 graphs you use, and then select whether you're going to use the solid line or the dashed line, and that's based on the material of your roof surface. All right, so if you have a shingled roof, that would fall under the all other surfaces category. You would use the solid line, and that would give you, like for a given roof slope, right, the solid line would give you a higher CS factor than the dashed line would, right? So if you have an unobstructed slippery surface, like those metal roofs that can allow the snow to just slide right off, you would use the dashed line. You would get a lower value for your slope factor, which means you're reducing those snow loads a lot more, right? And then once you've identified which of those 2 lines you're going to use, then you just read the value based on the slope. And I already demonstrated, right, the bottom of the graph provides the roof slope in degrees, but it might be more convenient to read it from the top, right, if you know your slope based on rise over run, right? So a 45-degree slope would be 12 on 12. Now, I highly recommend that when you use this chart, especially because it's conveniently or not so conveniently kind of small and hard to read, I highly recommend that you use a straight edge, better yet, right angle straight edge if you have one, to read values from this chart. So, just do your best when you are asked to do this in homework. I'm not going to be too picky that you get the exact right CS value. There will be an acceptable range of values that you can provide, but it should be within a reasonable range, right? So use a straight edge, and you should get a value that's within that acceptable range. All right, so there's a demonstration of that, reading the value. If you have a 45-degree sloped roof with a normal surface and a thermal factor of 1.1, your slope factor would be 0.72. So that's the other thing that's not so convenient about this graph is if you're using one of these charts, you have to read all the way across to this side, right? So that's another reason the straight edge is helpful. All right, and then I can use the top and so on. All right, well, that was pretty much perfectly timed because now we're primed for the handout. So I will just show you. We're not going to start it today. But on Monday next week, come ready for going through these examples, right? So there's a set of skeleton notes that is set up for these snow load examples, and we'll go through that. And then we will start talking about rain loads later. So let me find our schedule real quick so we have a minute. Yeah, so we'll be on track for the most part. We'll definitely finish up snow loads on Monday. We probably won't get through rain loads on Monday. Maybe we'll start rain loads. We'll see. And then between Monday and Wednesday, we should at least be getting through rain loads and load combinations and load envelope. And then on Friday, we're going to shift out of the structural loads portion of this class next week and start talking about influence lines, which is going to be a new way of thinking about the internal forces that a beam is subjected to for loading, different loading scenarios. So we'll start talking about that, and then we've got the exam following Monday. So we're moving through it pretty quickly. Any questions? No? All right, well, thank you all for your attention today, and I'll see you on Monday.